So, today we will be discussing the compaction in detail, and we have already studied a few points about compaction in the previous two lectures. So, now we will be beginning with the same topic that we have left in the last class, that is the factors affecting compaction. So, these were the four factors that were affecting the compaction, that is the water content, degree of compaction, method of compaction and type of soil. So, this first thing that we discussed, that was the water content. So, this water content was due to the, we discussed the lubricating effect here. Then if we talk about the degree of compaction, we also discussed this thing, that if there is light compaction test, then what happens if this is a heavy compaction test and the number of blows are increased to the soil. So, what effect will it bring on the compaction? Now, we will be discussing two more points here, that is the method of compaction and the type of soil. So, let us begin with the third one here, that is the method of compaction. So, whatever be the method, the values will be different. So, their effect will be somewhat different. So, the effect can be seen in terms of the weight of the compacting element, the time and area of contact between the compacting element and soil. So, if this is the soil here and let us say you have a rammer here, let us suppose. So, this rammer will have some contact area, this area will be the contact area. So, this if we place it on the soil for compaction, what happens, this the area between the area of contact between the compacting element, that is the rammer here, and the soil, and the action used for compaction. The different actions can be the pressure or the impact or the kneading or vibration. So, these are the four important types of actions that can be applied on a soil while compacting the soil. So, in the field the compaction can be achieved using the rollers, rammers or vibrators. Now, we will be discussing in detail these all the three things, wherein we will be discussing first of all the rollers, and in rollers, see here that it is something called as smooth wheeled roller. When we talk about the smooth wheeled roller, see the first thing here, then sheep foot roller and then pneumatic type roller. The second point was the rammers that we will be discussing, and the third point is the vibrators. So, according to the name, the many things we can derive about. See the first thing, that is a smooth wheeled roller. So, you have seen it in the field, like when you have seen the road construction, it is very common equipment there, this smooth wheeled roller. So, the action there is pressure, the pressure that it applies on the soil, that by that action, by the pressure action, the soil gets compacted. And next thing is the suitable, what type, this type of roller is suitable for certain type of soils. So, in this the crushed rock or the gravels or the sands, this smooth wheel roller is very much suitable. Now, for what type of project it is used and majorly used, so you already know this thing, that it is road construction. Now, if you talk about this sheep foot roller, so you have seen the sheep, their foot are somewhat like this. So, the if we say let us say this is a drum here, what happens here, these are some protrudings, in the shape of this. This is the 2D figure, it is a 3D figure, 3D thing, and this type of shape is called as sheep foot roller. The action is the kneading action, like you knead the dough. Duff means what? The let us say wheat flour that you are preparing. So, that thing, the kneading action is there. So, suitable for cohesive soil, and it is majorly used in preparing the core of earthen dams. Now, if we talk about this pneumatic type of roller, these uses both the pressure and the kneading actions, and it is suitable for all the soils, but they are preferred for cohesive soils because they are using both the actions. This is a multitasking equipment. So, for pressure also, for kneading also, both the actions are provided by this pneumatic type roller. They are used for base and sub base and embankment compaction for highways and also airfields. So, where there is a lot of amount of energy, compactive energy is required, lot amount of compaction is required, at that point also, like in airfields, at that point also pneumatic type roller is used. When we talk about the rammers, what happens there, you are like we started the discussion, that time we discussed what in labs we use some form of rammer. So, these rammers are similarly used in fields, but are of somewhat larger in dimension. So, these use the impact type of action, and these are preferred for all the types of soils, but major thing is for the cohesionless soils. And where the smooth wheel rollers, that is driven by some person, sheep foot roller and pneumatic type roller, these are driven by some people, but where there are not so much space at that time, in the confined spaces, in the confined areas, the rammers can be used. In the confined areas such as fills behind the retaining walls or the basement walls or the trench fills. So, in these places rammers are used. When we talk about the vibrators, their action is simply vibration, and you already know that cohesionless soil can easily get settled due to vibration action. So, cohesionless soils are mainly applied the vibration effect. So, when we talk about the embankment for oil storage tanks and similar other things, in that time vibrators are used. So, these are the different compaction equipment, and according to the situation, like whatever be the type of soil, we will be using some different element, different type of equipment. Now, moving on to the type of soils. So, understand here one thing, that if the soil is different, let us say it is a coarse grained nature or is it of fine grained nature, what happens when the different type of soil is there, let us say it is gravel or is it sand, or we can say is it clay or is it silt. So, when these different type of soil are there, then what happens there, at that point of time the compaction, the factors that the type of soil will be affecting the compaction. In what way, we will be seeing that thing here, but it is observed that for a set of soil, let us say GM, let us say this GM, for this soil the compactive effort is slightly more, and for this SM the compaction effort is slightly lesser than GM, and if you talk about this ML, so what happens, the compactive effort is slightly lesser. Now, see here that first we see the different types of soil. Let us see this GM, we have already studied and discussed these in detail when we discussed the classification of soils. So, this is GM is silty gravel, then we talk about SM, that is silty sand, that is sand which contains what, somewhat silt, some fines as silt. The gravel is there, but it contains some amount of silt. Now, if you talk about CL, CL is the clay is there and it is low compressible. If you talk about CI, it is intermediate compressible. If you talk about ML, so it is mainly silt, but it is low compressible. If you talk about CH, it is highly compressible clay, and for SP, that is poorly graded sand. So, see here we have observed these few values. For GM this is much higher value, for SM much higher value, and the OMC for this thing for GM is what, somewhat at a lower content, but for if you talk about this CI, that is the clay which is much more finer in nature, the fine soil will having what, see here more OMC here in this as compared to the gravel which contains some silt. Now, if you talk about this low compressible, see here the OMC is slightly much lesser OMC here, but if you talk about the intermediate compressible, what happens here, it is slightly much more here, and for CH it is not very much clearly defined, as you can see in the figure. For SP, it is a poorly graded sand, it is somewhat to this lower side. So, these are the different values, different graphs that we have plotted here. Now, according to these, there are some observations that we will be seeing. Now, understand one more thing, that as for some amount of fineness, if there is some amount of fineness, the gamma D maximum will try to increase, the gamma D maximum, this value will try to increase, the maximum dry density will be somewhat more, but when the fineness increases to a very much larger extent, the gamma D maximum tries to decrease. And second thing is the plasticity. What do you mean by plasticity? Plasticity is what, the ability to deform, but without the rupture, without breaking. So, when the plasticity decreases, then gamma D maximum also decreases. So, these 2 points are there that you have to remember. Now, we will be going for some observations. Now, see here, see the coarse grained soil well graded compact, when compacted to high dry unit, they will be see again the coarse grained soils, that is which are well graded, they compact to high dry unit weights, especially if they contain some fines, that I have already told you that if they have some fines, they will try to compact to a higher dry unit weight. But what happens if the fines are in excess? Then the maximum dry unit weight decreases. So for a certain amount of fine it is okay, but later on what happens, the maximum dry unit weight will be decreasing. So that will not be very much beneficial for us, because in field we try to find out what will be the maximum dry unit weight that can be achieved. So because that will be making the soil more and more stable. Now taking the second point here, poorly graded or uniform sands, you have already studied what is poorly graded, what is uniform sand. They lead to the lowest dry unit weight values. Okay, so these are not resulting into proper compaction, because the dry unit weight which we want to achieve is slightly much lesser value in these type of sands or in the poorly graded soils. In clay soils what happens? In the clay soils the maximum dry unit weight tends to decrease here as the plasticity increases, that we have discussed. Now when we talk about the cohesive soils have generally high values of OMC, that we have seen in the graph there. Then heavy clays with high plasticity have very low maximum dry unit weight and very high OMC. Remember this thing, that these things are, this gamma D value is slightly lesser and OMC is slightly more. So the graph shifts to the right side of the graph shifts to the slightly right side here and to slightly lower value here. Okay. Now after we have discussed the type of soils, now we will be moving on to the numerical here. Now see the question, compare the compactive energy used in IS heavy compaction test with that of Indian standard light compaction test. So these are two tests, heavy compaction and then light compaction. We have already seen this two things. Now what happens when you compact the figure, when you compact the soil, you impart some energy there to the soil, and with that energy the soil gets compacted. So see, in the IS heavy compaction test, what was there? There was some different specifications for conducting the tests. So in this test what did you use? You used the 4.9 kg rammer, you compacted the soil in 5 layers, and in each layer you provided how many number of blows? You provided 25 number of blows. Acha, what was the free fall height of the rammer? Let us say you took the container here and in this container you put in the soil and then you took the rammer here. So what was the free fall height? This was the somewhat free fall height. So this free fall height was 0.45 meters. So you know this data because you have already performed this experiment, IS heavy compaction test. So and then we take the per meter cube energy. So when you talk about this energy, what comes out to be 2,75,625 kilogram force meter per meter cube. So this is the compactive energy which is used in IS heavy compaction test. Now see here, when we are talking about the light compaction test, what happened there? In that case we used a 2.6 kgf hammer. This light compaction test we use slightly lesser weight of hammer, so that was there 2.6 kgf. Then the free fall height was 310 mm, that you have to remember, because while doing the numericals, 310 mm of the free fall height, that is 0.31 mm, and you compacted it in 3 layers, and in each layer you provided 25 number of blows. And when we talk about per meter cube, it comes out to be 60,450 kilogram force per meter cube. Now what is the question? Now you have to compare the compactive energy used in IS heavy compaction test with that of IS light compaction test. So the compaction value for this is V is 2,75,000 something, and for this is 60,450. When you take the ratio of this thing, it comes out to be equals to 4.56. The ratio comes out to be 4.56. So this you can simply understand that the energy provided in the IS heavy compaction test is 4.5 x, that means 4.5 times this one, if this is x. So this energy provided in the IS heavy compaction test is 4.5 times more. So this is the ratio, and the amount of this compactive effort that is there. Now moving on to the next question, the compaction of an embankment is carried out in 300 thick layers. The rammer used for compaction, so there is no smooth wheeled roller or something or vibrator, nothing is there. The rammer is used for compaction, has foot of area 0.05 meter square. The energy developed per drop of rammer is 40 kilogram force meter per meter cube. So this is the energy that is developed there. Now assuming 50% more energy, okay, see this thing, this is important here. In each pass over the compacted soil, over the compacted area due to overlap. I will tell you with a diagram here. Now calculate the number of passes that are required to develop the compactive energy equivalent to IS light compaction test for each layer. Now understand, let us say if this is the data given and you have some rammer here which has a foot area. Now this area is what, 0.05 meter square. Now the energy developed per drop of rammer, like each time you drop the rammer on the soil, what is the energy that is developed? That is 40 kilogram force meter per meter cube. So the energy is given. Now it is carried out in 300 layers or thick lifts. Now see here, if let us say in the figure C, let us say this is the sand or the soil which is there, and the roller is being applied in this portion. So what happens, the next time what will be there, the rammer, sorry, it was not the roller, it is the rammer which is being applied here. Now in the next pass, okay, in the next pass what happens, this 50% area is also covered. So this 50% area will be also covered in the next one. In the first one it was this much area, so in the next one, so this portion, if you talk about simply this portion and this one, what happens in this portion, it is compacted twice, it is 1.5 times more energy is given, like first was given, then again what happened, due to 50% more energy was imparted to this area. Now you know already that compactive energy used in IS light compaction test is 60,450 kilogram force per meter cube. Now you can easily solve it, I have not shown it here, but in the previous numerical you have already seen, like this thing that 2.6 kilogram force into 0.31 meters into 3 layers into 25 blows per layer by the area, that is the 1 meter cube, that is the 10 to the power 3 into 10 to the power minus 6 meter cube. Now see here, so the value comes out to be 60,450 kgf meter per meter cube. Now you already know that the energy that is to be imparted is what, 60,450 kilogram force meter per meter cube. Now so the compactive energy per drop provided by rammer per cubic of soil is what, 40 kilogram force, that is by the total, okay, by 0.05 meter square into the this lift, that is the this much thickness is there of the soil. So this is the area, so this is the total volume that is being provided, that is being imparted the compactive effort. So this comes out to be 2666.67 kilogram force per meter per meter cube. So however in each pass 50% more energy due to overlap. So overlap was there, that I showed you in the figure. So at that times, so actually if we consider the n number of passes are there, so we will be taking 1.5 times of that n into, for each pass it is 2666.67 kilogram force meter per meter cube. So that will be equal to what, the final energy that has to be imparted, and the final energy that has to be imparted is equal to IS light compaction test, which is given in the question here. So n comes out to be 15.11, so we can round it off, and 16 number of passes will be required for compacting the entire soil by the rammer. Now we will be looking on to the into the new area here. Now we will be studying the effect of compaction on the engineering properties. So see what are the engineering properties that will be getting affected here. the structure, the permeability, water deficiency and the pore water pressure. Then we talk about the shrinkage and swelling, then we will talk about the compressibility and the strength. Now if compaction is done, so what will be its effect on the engineering properties, that we will be studying in this topic. Now see the very first thing, the structure. We have already studied the structure when we talked about the clay mineralogy and soil structure part. So see here, at the same compactive effort, with increase in water content, soil particles get more oriented. So see in this figure here, that with the same water at same compactive effort. So these, if this is one gamma d and this is the water content on x axis, gamma d on y axis. Now let us say when we prepared the graph, I told you that this graph is for one type of compactive effort and this graph is for another type of compactive effort, this second one, this first one is from another. Now see, if for one type of compactive effort, so we will taking this soil. So what happens, this is the OMC, let us say the optimum moisture content for the first type of curve here. Now if you talk about when the water is less here, at that time what happens, this is somewhat less oriented, this one is less oriented, see the figure, see this is what, less oriented. But when we increase the water content, what happens there, the soil particles tend to get more oriented. So that we have seen in the point number 1, that at the same compactive effort, जैसे जैसे पानी बढ़ता चला जाएगा, what will be there, the soil particles will tend to get more oriented. Now here at same water content with increase in the compactive effort. Now see, at same water content, let us see if this is the water content that we are studying here, let us say W dash, at this water content with increasing compactive effort, okay. So when we are talking about this B point here and then this D point here, what happens, when the compactive effort increases, then soil particles are observed to get more oriented. So see in this B there are some oriented particles, but some are there which are not yet oriented. But when we increase the compactive effort, what happens, see in this figure, more and more particles tend to get oriented. So D is more and more oriented, okay, it is more oriented. Okay, let us see one more, you can see this. Let us see if we take this point here and we say this is W double dash, another water content that we are seeing. See here that at this water content, at some amount of compactive effort, this value was there. Now if we increase the compactive effort, what will happen, the soil particles which were very much less oriented here, they will tend to get slightly more oriented, okay, they are not getting oriented just like this thing like D portion, but they are getting slightly more oriented than that of A. So as the water content is increasing, there was at the same compactive effort, soil particles get more oriented, and the second point, at the same water content we discussed, with increase in the compactive effort, soil particles were observed to get more oriented. So we have seen the A and C points there and then B and D as we have compared. Now at the same compactive effort, see the third point here, at the same compactive effort, structure of the soil is flocculent on dry of optimum. When now see what is dry of optimum and what is wet of optimum. So see here, when we talk about this graph, this is the optimum moisture content. Now when the water content is slightly less than this thing OMC, then it is dry of optimum. So this is the dry side. But when we talk about the water content more than OMC, what happens there? It is the more water is there, so it is the wet side here. So on the dry side, structure of the soil is found to be flocculent, and when you talk about the wet side, it is the structure is found to be dispersed here. And in terms of orientation, you already know that A was the least oriented there, and then C was slightly better reoriented, see this point due to this point, okay. And if you talk about B and D, with the very first point you can say that B is slightly more oriented than A, okay, and you already know that D is the best oriented, okay. So we can say that A is the least oriented here, and then D is the best orientation, having the best orientation of the particles. Now, if we talk about the permeability, see here that at the same compactive effort, what happens with the increase in water content, permeability of the soil sharply decreases on the dry of optimum. Now, second point to understand here, when we talk about wet of optimum, so this was on dry of optimum. Now, what happens on wet of optimum? With the increase in water content, when we increase the water content beyond what? OMC, what happens? The permeability will first of all increase, but then it will start decreasing. Now, understand another sub point here, that even after the initial increase observed in permeability. So, let us say this is the curve, and if you are talking about this thing, this is the OMC, okay, and this is the gamma D value on the y axis, and W on the x axis, the water content. So, see here the very first point, that at the same compactive effort, okay, same compactive effort we are moving, and this, if we are talking about the dry side, what happens in the dry side? The permeability decreases sharply, but when you move on to this point, the wet side, what happens here? The permeability will first of all increase, but then it will try to decrease, it will be decreasing there. Now, so even after the initial increase observed on the wet side, that we are discussing the wet side here, the permeability will be comparatively less than the permeability on dry of optimum. At the same water content, if you are talking, with increase in the compactive effort, permeability of the soil decreases due to better orientation of the particles. So, the particles will tend to get more oriented at the same water content when we talk about the different curves here. So, this point, this third point, you can simply see in the this thing, like if there is one compactive effort, and then there, if your compactive effort is increased, let us say you are applying the heavy compaction test, so it comes out to be somewhat more. At this water content, if you try to see, then this third point will be valid. So, the particles will tend to get more oriented. So, as the particle tend to get more oriented, the permeability will try to decrease. So, we have seen there that the structure is flocculent here on the dry of optimum, on wet of optimum it is dispersed, and for permeability it is more on the dry of optimum and it is slightly less because of the better orientation. So, here the permeability is slightly less. Now, we will be discussing the next few effects of compaction on the engineering properties in the later class. Thank you.